Good morning. Welcome to Krishna's classroom. In this lecture, we consider two extremely important inequalities in the study of LP spaces. And they are the Holder's inequality and Minkowski. You would have heard about the Kozhikode inequality. That's a special case of the Holder's inequality, or Holder's inequality is a generalization of the Kozhikode. With the choice that p equal to 2 gives you the Holder's inequality with the choice p equal to 2 gives you what is called the Kozhikode inequality. That we shall make a mention of it at the end of this lecture. Now, the Holder's inequality is a tool in proving the Minkowski. So we will just work on this theorem. So we state first we consider the Holder's inequality. I also want to tell you that this contains much more information than what is outwardly visible. In fact, when we consider the non-linear spaces and then their dual spaces, then you see that the significance of this Holder's inequality. Okay, so we have seen that 1 less than or equal to p less than or equal to infinity, and for 1 less than p less than infinity, q is the conjugate number satisfying satisfying 1 by p plus 1 by q. Now q is uniquely determined and q also belongs to q is called the conjugate of p, and vice versa, that is p is the conjugate of p. Okay, so that relation is there. For p equal to 1, q is defined as infinity number. Also, for p equal to infinity, q equal to defined as 1 as the conjugate. So these two things are well defined now. Now we are in a position to state the Holder's inequality as a theorem. Let E be a and Q if F belongs to L, E, E and G belongs to L, Q, E, which we have defined earlier, then their product Fg, F times G is integrable over E and is P norm of F times Q norm of this is the Holder's limit. Moreover, if F is equal to 0, then of course you know that Q is infinity. Oh, sorry. Moreover, if F is not equal to 0, then the function F star defined by norm of F is P norm of F to the power 1 minus P into sine of signum function F times modulus of F P minus 1. This is well defined. Belongs to LQ and integral over E F times F star is equal to norm of F Q norm of F star is equal to 1. Or in other words, equality holds in the Holder's inequality. That so we will make a remark about that at this stage and then later revisit the whole. make a remark on that. The second part of the theorem shows that if f is not equal to 0, and of course f belongs to then there exists an f star equality holds. Which in turn implies that this inequality cannot be improved upon. Okay. So there are situations, or there exists f and g such that the equality holds in the holders inequality. So that's a very special situation that we have. Okay, so one cannot think of getting a much better estimate for this. Okay, so now we will so with that remark, I think I'll revisit this remark again after proving the theorem. So we make a further remark. Signum function is defined as 1 0 equal to -1 if fx is x. So wherever the function f is non-negative, the corresponding sign function is equal to 1, and wherever the function is negative, there the signum function takes the value -1. So that we remember, I mean, it's a very well known fact. Now we try to prove this theorem. So let us first consider the case we take p equal to 1 and q equal to infinity. So what we have is f is an L1 function and g is an L infinity. then f is and we have G is L infinity E means the essential supremum of G on E is bounded, okay, or G is essentially bounded on E. Now let us estimate this. Essential supremum of G times mod and which is equal to now let us look at the what is the status of the second part. Further, F star is equal to, this is the definition. So to the power 0 because 1 minus p equals 0. Sign. Because 1 minus p equal to 0. Okay. Now this implies signum f is an L infinity function. Well, it's a bounded function. This is either plus 1 or minus 1 absolute value of. So it is bounded by 1. And therefore it's equal to 1. And the 7. That is so we have constructed verified that f star is an empty function. Now consequently mod f, so G we take as f star, this is equal to norm of this. I am just applying the definition 0 0 because P equal to zero. That's the reason. Which implies mod f star equal to but which is equal to 1. Therefore, to see that the equality. So we have constructed an f star in this case, and we have shown that integral f star is equal to norm of L1 L infinity such that So that is proved for the case P equal to 1. Now we take up the case where P is not equal to. P greater than. If F or G zero element, namely F is 0, then we will integral over E equal to 0 So one of the factors is going to and other conditions are of course assumed, that is F belongs to LP, G belongs to LQ. These are of course basic assumptions. Now what happens to this? In such a case, suppose F is not equal to 0, then F star is defined as so that's the definition of F star. Now what happens? Therefore we will compute this one, F star integral. So first of all, is F star in LQ? That's the question. This is the question that we are asking. Okay, so let us compute this. So let us compute this. Let us compute this. And that is equal to F star Q, let us work on this. Use the definition. Now this becomes we are taking the qth power and then taking the absolute value of that. Therefore, signum F is 1 and you have mod F to the power Q into Q minus. Whole thing, the power. Now you see that this Q into 1 by P or Q into 1 minus P, just work out that. What you have is 1 by P plus 1 by P. It implies Q equal to or P equal to Q into 1 minus. Therefore, Q into 1 minus therefore this is equal to E. Now you see, by the assumption that F is LP, these are all well defined. And this is equal to, this gives, and we have taken F not equal to 0, that means the norm of that is not equal, or that means this integral is not equal to 0. Therefore, let us work. This is equal to. So that is clear. So norm of so we have proved that. Now what we want is, therefore F star belongs to LQ. And we have also calculated this. Now assume that Therefore, what have we obtained? So our main statement was this, that is integral fg. Okay, what did we assume? Yeah, we have already verified. Now we assume that this is true. F is not equal to 0. G is, both are not equivalent, or both these functions do not represent the zero element, and therefore in LP and LQ respectively. Now first observe that Holder's inequality is true, or rather suppose we that. Just assume this. Further, let us assume that equal to 1. Assume for these functions then we have integral over E less than or equal to 1. Okay. Now let us take f to be any function in LP and not equal to 0, and g to be and not equal to 0. Then f divided by norm of the P norm of this equal to 1 and norm of G divided by the Q norm of this equal to 1. I mean, they are easy to do. Okay. So, what is the outcome? Therefore, so let F tilde be F divided by G tilde then by our assumption integral over E mod F tilde because they are normalized functions. The norm of F tilde equal to 1, norm of equal to 1. Then this is true, which implies we use this integral over E you assume that F and G are not okay. Therefore, the proof is complete if we for F belonging to LP with the norm of F equal to 1 and G belonging to LQ and G belonging to LQ and for G belonging to LQ with the norm of G equal to 1. And I should not call it norm at the moment. Not yet. We have that's the one that we want to since and over E we have F and G finite almost everywhere that means except possibly on a set of measure 0 F and G is finite. Okay, so that's enough. Now we apply inequality. What do we have? Then we have mod G, and that is less than or equal to Q almost everywhere on E. So this inequality is the application of, see, at every point you are applying this inequality, Young's inequality, because they are numbers. See, f dot G at x, some x is, this is evaluated at fx, mod fx times mod gx, and that is less than or equal to mod fx to the power p by p plus mod gx by the power q by q wherever they are finite, and at points we ignore the points where they are not finite. You don't have to consider them because such a set of points is of measure 0, therefore it doesn't affect the. Therefore, integral over E is less than or equal to 1 by P G to the power Q. And since equal 1, we have so we have proved this inequality, and the consequence of this is that for normalized functions you apply this, and from that you get the general inequality. Okay, so that's it. Now we work out what is F star. Now F star, you recall the definition of F star is in the second part. We call minus 1. Okay, so that's the definition. Therefore, we compute F star. So F star equal to this is equal to one minus p into f to the power, where we have used the fact that this is almost everywhere on, because we have this one sine of f multiplied by mod f to the power p minus 1 plus into mod f, that will give you mod f to the power. That's how you get it. And therefore, p, and that's equal to to the power 2, and that's equal to, so that we have, and q into p minus 1 equal to p, therefore f star, this is equal, that you can easily. So we have completed the proof of this theorem. Okay. We make the remark. For and f not equal to 0, the function f star is called the conjugate function of f. Now, what is the significance of x? So let us write. What we have proved is this. F not equal to 0, there exists an f star belonging to L Q such that what is the significance of that? This means that one cannot think of an improvement is getting more sharpness. Hold this meter. And that's the best possible inequality. is the best form of unless you can't improve upon that. If it were possible to improve, we would not have, there could have been a gap. That's one could have proved this. That is, one cannot prove one say it is not true that strictly less than for every f comma g, f belonging to LP and g belonging to. Now that is this is the sharpest possible estimate of integral f dot g, which has lot of significance when we work on or when we start probing the structure of LP more deeply, which is not what is intended at the moment. Now we go on to prove the Minkowski, where of course our purpose of Holder's inequality at the moment was very limited to apply in proving the Minkowski. So let us work on Minkowski. Let us state the theorem. Let E be a measurable subset of R and 1 is if LP, then what we have is 1, you can write then f plus g also and further this is the Minkowski, very significant, which is a vital ingredient in proving that norm of f p is essentially the norm of f. It's called the LP norm. So let us prove this. For p equal to 1 and p equal to infinity, we have already proved this result. And what is it? We have proved that and these two inequalities we have already. So let us assume so for this we prove the result. Okay. We have the inequality. We have for A, comma B, mod A plus B to power P is less than or equal to 2 to the power P now this we have to prove for these two numbers. That's something where we have to prove the result and then we shall use that. So we are not going to. Consequently, what we have is almost everywhere on this is it. Step 1 second. Is finite. Finite. Because each of this is now, so if F belongs to LP, G belongs to LP, then F plus G belongs to, that is now we will estimate this. Now assume not equal. If F plus G equal to 0, then of course to see that this integral is 0 and therefore this inequality is automatic. Trivial. So assume F plus G is not equal to 0. That means almost everywhere. Then what we have is compute F plus G star. This is equal to 1 minus 2 by definition NISER. Now this we know, this belongs to LQ plus by what we have proved already. Okay, the star, if F belongs to LQ, then F star belongs to LQ. So we compute this. This is equal to integral over E, we calculate this. F plus G star is F star is this one. This is what we have computed, and you just use this. You multiply by F plus G, and then you compute the whole thing. Now this is equal to, so we can split this. So we apply Holder's inequality. What we get is the following. This is less than or equal to so you get the, now we know that if F is not equal to 0, then F star has the Q norm of X, that is the norm of norm G norm C F. Well, this result we use. Therefore, which implies consequently norm of so that completes the proof of the Minkowski. Okay, now we will explore the consequences of this result and also the special case of Cauchy-Schwarz inequality in our next lecture. So, thank you very much.